recording. Yeah, it's my great pleasure to introduce Soonwon Choi as this week's QFarm speaker. Soonwon did his PhD with Misha Lukin at Harvard, and he's currently a Miller Fellow at Berkeley and will be starting his faculty position at MIT in the fall. Soonwon's work occupies this really interesting space that kind of straddles theory and experiment in equal measure, and also straddles kind of AMO physics, quantum information, condensed matter. So it's a very kind of creative area to be in, and I think the work that Soonwon will be telling us about will similarly also include both theory and experiment, and some pretty like fundamental questions in quantum information. So yeah, Soonwon, why don't you get started?
Thank you very much, Vedika, for a nice introduction. I really appreciate it. So let me share my screen. Yeah, so it's good. Okay, so let's get started. Once again, I would like to thank the organizers of QFarm seminar for giving me this opportunity to talk about my recent work on emergent quantum randomness and quantum device benchmarking. My name is Soonwon, and I'm currently a Miller Fellow, postdoctoral fellow at Berkeley, but starting from this June, I'll be moving to MIT as an assistant professor. So before I start, I would like to emphasize that this work was done in collaboration with the many people. Especially, I would like to emphasize the theory collaboration with Jordan Kurtler at Harvard and Daniel Mark at MIT and Robert Huang at Caltech. And also I'll present some experimental data which was taken by Junhee Choi and Adam Shao and Manuel Andres. So all of us contributed to the theory altogether. So my talk, I'd like to begin by celebrating statistical physics. In this field of study, we talk about, we consider the physics of many particles, like Avogadro number of particles, and we are interested in their collective macroscopic behavior. Surprisingly, there are many different types of universal phenomena that occurs. And for those universal phenomena, this statistical physics allows us to make predictions with extremely good accuracy. So what do I talk about by universal phenomena? And examples of them include quantum or classical thermalizations. Independent of the initial state, we know the system will eventually equilibrate. Or quantum or classical phase transitions. If you tune certain parameters of the system, temperature, pressure, or the strength of the terms in the different Hamiltonian, the system undergoes macroscopic dramatic change in their properties. And more recently, the statistical physics has started become actually the foundational principles to understand the interplay of the gravity and then information, the quantum mechanics and the classical gravity, essentially. So maybe I should not emphasize too much about like statistical physics, because everyone understands that the statistical physics is an amazing field of approach to study physics. Therefore, it's natural to ask why and how the statistical physics works so well. This is an active field of research, but in the classical systems, classical physics, there's a well understood, it's just still like under research, but there's a widely accepted explanations for the emergence of statistical behavior, and that's essentially chaos. So if you consider two different initial state of the many particles, say they look identical except for maybe a small kick in momentum of one of the particles, and consider their natural time evolutions, chaotic time evolution. And then what we believe is after relatively short amount of time, the particle configurations in the phase space becomes completely different for the two different cases. And this is so-called butterfly effect. And there's a very important consequence of this butterfly effect for studying statistical physics. In any realistic situations, we never know everything perfectly. We always have a little bit of imperfections about the information on the initial state of the system. And you can think of this imperfect information as if each particles are perturbed by a little bit for the unknown perturbation. Therefore, in this case, if you consider the time evolution, those small perturbations effectively get amplified and we lose information about the initial state. Therefore, independent of the microscopic details, the later time behavior of the system can be described by essentially random distribution. What's interesting is this random distribution has a universal properties. For example, independent of the microscopic details, this ensemble is described by and parameterized by a few extensive variables such as volume or temperature or chemical potentials. And because of this emergence of universal ensemble, we can use the statistical physics to analyze them. So let me recap the logical flow. We have a chaotic dynamics, which leads to the loss of information. And this loss of information is the same as the emergence of certain universal random ensembles, and that's how we can use the statistical physics. If we try to apply exact same logic to the closed quantum many-body system, and now the situation is slightly different. First of all, let's consider the perfectly closed many-body system that undergoes Schrodinger's equations motions, which is a unitary evolutions. And in this case, any small perturbation on the initial wave function will not get amplified over dynamics because of the unitarity. The small perturbation will remain small. So instead of using this classical butterfly effect paradigm, we tend to look at the quantum chaos or thermalization from a slightly different angle. And there are two widely accepted perspectives. One is using the notion of quantum entanglement. Even if we consider a globally pure many-body wave function, if you are only interested in small enough subsystems, the reduced density matrix of subsystem can be described by a mixed state rather than the pure state. And that's because the subsystem is entangled with the rest of the system. In other words, unless we know the global system, there's a certain bit of information that we cannot recover. And this delocalization of information or correlations allows us to have emergence of randomness. The second approach is the theory approach based on the random matrix theory. So in this approach, we make a conjecture. The conjecture is the following. If you consider the Hamiltonian of a chaotic system, and suppose we exactly diagonalize this Hamiltonian and consider their eigenvalues and eigenstates, and the conjecture is that those eigenvalues and eigenstates of physical Hamiltonian looks very similar to that of random matrices drawn from some universal ensemble, like Gaussian orthogonal ensemble or Gaussian unitary ensemble. And therefore we can use this emergent randomness. We can use these properties of these random ensembles to make a prediction about the system. And these two perspectives are complementary one another and has pros and cons. For example, the quantum entanglement picture provides a good explanation of how thermal state could emerge as a subsystem because of delocalization informations. However, it does not have that much of predictive power because once we know the answer, we know the answer, but before knowing the answer, it's how to make a prediction. On the other hand, the random matrix theory has a very strong predictive power. However, here the emergence of randomness, which is in my view the gist of the gist of the problem, where we can use the statistical physics, has not been explained well. So it does not talk about why this randomness emerges. So what I'm going to talk about today is a new approach that's maybe somewhere in between these two approaches, or maybe complementary to both. And the idea is we consider the emergence of random ensemble even if we consider the globally pure state. And the take-home message I would like to deliver today is that even if you consider a single many-body wave function, this wave function could encode a random ensemble quantum state, and we can use statistical toolset for those random ensemble. And the next item I want to emphasize that now that we can study the random ensembles, we will show that those random ensemble will actually exhibit a certain type of universal behavior under certain conditions, so-called the quantum state K design. I'll try to unpack what I mean by quantum state K design in the later part of the talk. And then I'll present the experimental signatures by using the Ripple-Gatten quantum simulators. And finally, using those universal signature and the new observable universal phenomena, we'll design a quantum applications, practical applications to benchmark analog quantum simulators, and then also talk about the experimental demonstration of that. So with that, let's start from the the emergent random ensembles. So now the question is the following. Given a single many-body wave function, maybe this many-body wave function is obtained from random unitary circuit, or time evolution, the quantum time evolution starting from a certain initial state, or maybe we take an energy eigenstate of certain chaotic Hamiltonian. Can we talk about the degree of randomness for this wave function? And in fact, this question may not be well defined for the classical settings. For example, let's consider an analogous problem where we are given a binary bit string, a certain bit string, and ask whether this particular bit string is random or not. And this is not well defined because randomness is not a property of a bit string, it's a property of generating a bit string. So, however, in the quantum mechanical problem, this question still can be well defined, and that's because there's an intrinsic randomness in quantum mechanics, and that's the probabilistic behavior associated with measurement. So let's for now consider the following situations. We are given a many-body wave function psi, and divide the system into the two parts, the one part A and the rest of the system B, and consider performing local projective measurements on all qubits in subsystem B. And we'll get some measurement outcome, for example, is 1001000, and the wave function will collapse for the subsystem part B, but the wave function on the subsystem A will remain in a certain pure state. And this pure state depends on the measurement outcome on the part B. If we repeat the same procedure again, we may end up getting the different measurement outcome in B, say 0001110, and then the subsystem A will remain in general distinct, different pure wave function psi A, again depends on the measurement outcome, and so on. In general, if the size of B is so large, so it contains like NB qubits, we can generate in this way a 2 to the NB distinct quantum states. And these all quantum states are associated with a certain probability of getting that state, essentially the probability of getting a certain measurement outcome. Therefore, we can define an ensemble of pure states where the state is enumerated by the different measurement outcome on B, and each quantum state on A is associated with the probability of measuring that bit string. And we call this ensemble a projected ensemble. In this way, what we have done is the following. We are given a single many-body wave function, but now we define an ensemble of pure states defined for its subsystem A. In general, there are so many different states, and the number of states could be larger than the dimension of Hilbert space for the subsystem. Therefore, this wave function need not be orthogonal to one another. So they could have a finite overlap, but in general, those wave functions will not be perfectly equal to one another. So we'll have a distinct set of wave function. Okay, once we have a ensemble of state, now we can utilize statistical tools to analyze them. For example, the simplest statistical statistics of the ensemble would be the mean, the first moment. So first moment, what I mean by the first moment is that we draw the wave function from this ensemble with the probability P, and then compute the weighted average of the density matrix associated with each state like this. And turns out this first moment is exactly equal to reduced density matrix of the whole system. And we know that if the global wave function was drawn from physical wave function, for example, right after the output of the random unitary circuit or the quantum dynamics, we just talked about how this reduced density matrix will approach a universal value that's only characterized by, for example, conserved quantities such as the temperature. So what we know here is that the first moment of this ensemble approaches certain behaves in a universal way, independent of the details of the initial wave functions. The mean value of the ensemble approaches the same value. But now we can consider the higher moments as well. So what if you take the wave function and raise it to the power of tensor 2, and then average over z. So this is a second moment of the wave function, and this is different from reduced density matrix. However, we raise to the third power and then average. That's the third moment of the wave function, or the kth moment of the wave function. The question is whether those higher moments also exhibit the universal behavior or not. But generally, we can ask how uniformly random the quantum state ensemble is how uniformly randomly the ensemble is spread over the entire Hilbert space, more abstract questions. And the notion of quantum state K design is defined to characterize those properties. So let's just make a short detour to talk about the quantum state K design. So quantum state K design is a concept introduced in quantum information theory and mathematics, and the definition goes as follows. We consider an ensemble of quantum states, and we say it is a quantum state K design if all its statistical properties up to the kth moment matches with those of a Ha random ensemble or uniformly random ensemble over the entire Hilbert space. In other words, it simply characterizes how uniformly a random ensemble is over an entire Hilbert space. So let's take an example. Consider the Hilbert space of a single qubit, so two-dimensional Hilbert space, and we consider an ensemble of pure state, which is made out of two states, like 0 or 1, or in the spin picture, it's up or down with the equal probability, 50-50 probability. If you consider the first moment of the ensemble, that's the reduced density, the density matrix, we know that it will form a 0, 0 plus 1, 1, and that's the maximally mixed state. And the maximally mixed state is the same as the mean value averaged over whole Bloch sphere. And in this case, we say this ensemble of a pair of states forms a one design. But let's say we consider the second moment. And we know this second moment of the wave function is not equal to that of Ha random. And this is why. For example, let's consider the expectation value of x, evaluated x operator, the polarization along x, for these two different states, 0 and 1. In both cases, the expectation value is precisely 0. So the variance of the expectation value along x over a different quantum state is precisely 0 because they have the same value. However, if you average over all uniform ensemble over the entire Bloch sphere, we know the variance in the expectation value of x won't be 0. Likewise, if you calculate the expectation value along z, the polarization along z, we know that this ensemble has a larger variance than those of Ha random states. Therefore, they have a distinct statistical property starting from the second moment or the variance. Turns out if you use like ensemble of four pure quantum states distributed at the corners of a tetrahedron, we can show that this ensemble matches not only the first moment, but also the second moment of any statistical property, up to second moment. And furthermore, if you introduce more and more quantum states, we can design the ensemble of pure states so that they are identical to the Ha random up to higher moments. And in order to achieve the Ha randoms, we need to match all moments to k goes to infinity. And in order to do that, we have an infinite number of states. So in short, if an ensemble forms a higher k design, that's essentially saying that this ensemble is more uniformly random in Hilbert space. We can define this notion of quantum state K design for the many-body wave functions. So in this case, let's consider the many-body Hilbert space for the n qubits. And if you have random state, randomly distributed, finite number of states randomly distributed over the Hilbert space, and it's considered like 2 to the n number of randomly spread states, and we say we know that this ensemble will form approximately one design. If you have a 2 to the 2n randomly spread states, and those will start forming approximate to design. And in general, if you have a 2 to the kn randomly spread states, they will approximate the Ha random up to the kth moment. Having large number of states is not sufficient to form a high design. For example, even if you have like many different quantum states, if their distribution is not uniformly spread in the Hilbert space, but somehow concentrated around a certain corner, and then we know they do not form design. More formally, given an ensemble, we can systematically calculate whether the ensemble forms a K design or not. And the way is to calculate the kth moment of the ensemble. Say you raise up the wave function to the power k in the tensor product, and then average the quantity over a given ensemble, and compare this quantity against the moment of the true moment of the Ha ensemble by measuring their distance in L1 norm. And we will use the notation delta k in order to measure the distance between distance in the kth moment of our ensemble against the Ha random ensemble. So let's come back to our original picture. So we have many different interesting wave functions, and we described how to generate an ensemble of pure state for each subsystem. And then we talked about that the first moment already converges to a universal value due to quantum thermalization. But I'm going to argue that also the second and third and kth moment converges to a universal value as long as the global wave function is associated with the infinite temperature state, or for the systems that energy is not a well-defined quantity, the energy is not conserved. Namely, we'll argue that the higher moment will converge to the kth moment of Haar random ensemble. So, do you have any questions? So I think for the 1 hour talk, I have not like dense slides, so I'll be happy to answer any question if there is any. Okay, otherwise let's proceed. So for the next few slides, and actually for the main part of my talk, I'm going to go over many different examples, and I'll present evidence supporting our claim. First of all, we show that in fact the projected ensembles generated from almost all quantum states form approximate K design. So let me illustrate what I mean. So consider the n-body many-body Hilbert space and choose some random wave function, uniformly random wave function from it. And starting from this wave function, we consider the subsystem projected ensemble. And my claim is this projected ensemble will form approximate K design. And this statement is like, I want to emphasize that this statement is not averaging over like randomly picked global state, but a single wave function and their projected ensembles, we still have our approximate K designs. And this statement can be formulated as a theorem. In fact, as long as the subsystem A is sufficiently small compared to B, we can form this approximate K design with extremely high probability. And what it means is that, in fact, like almost all quantum state in the Hilbert space satisfies our claim. So this was nice results proving the generality of our claim. However, sometimes this is not as physical as we believe. If you choose a random state from the many-body Hilbert space, sometimes those wave functions is not as physical because they have usually very high complexity. In fact, many of the physical quantum mechanical wave function is concentrated on a special corners of the Hilbert space, for example, where the entanglement is sufficiently small, or the complexity of the wave function is sufficiently small. Therefore, even though the theorem shows that generality of our claim, maybe this is not really relevant for our physical situations. And in order to address that, we actually proved another statement. Instead of considering almost all quantum states, we consider a large class of efficiently preparable quantum state, efficiently preparable using the quantum devices. For example, let's consider a random unitary circuit, a typical output of random unitary circuits, or typical output from a time-dependent Hamiltonian evolutions where there's no particular conserved quantities without any symmetry. And we claim that, we prove that any typical output from those ensembles generates a projected ensemble for each subsystem that also forms a projected approximate K design.
May I ask two questions? One is, what's your definition of a typical output? And the other is, what's the definition of an approximate K design? I believe you should have some formulas like involving epsilon, something like that.
Yeah, that's right. So what we say typical is we consider, for example, a random ensemble of random unitary circuit. And then with the probability larger than 1 minus delta, the projected ensemble generated from that wave functions forms a K design, epsilon approximate K design. And we bound the epsilon and K from the size of the subsystem and as a function of delta.
So when you say epsilon, so like in the definition of K design, you calculate some expectation value. So when you say epsilon K design, does that mean that I allow the epsilon error in going away from that expectation value from
exactly right. So So we say on ensemble forms approximate K design rather than the exact K design if the kth moment is close to the kth moment of the high random state up to epsilon correction in L1 norm.
Yeah, so how about the typical output? Like how do you, well, what's the measure? Like, do you calculate the entropy of the projected ensemble and allow epsilon difference to consider that's your typical output, or you use the other definitions? I'm just curious about it.
Yeah. So when we say the typical output, we say the probabilistic, we make a probabilistic statement. We choose a state from an ensemble of random unitary circuit. And the probability that each projected ensemble forms an epsilon approximate K design is larger than 1 minus delta. And delta is very small.
Okay.
Yeah, actually here is the theorem too. So I'm not going to go over this because it's just lengthy and not so illuminating. But the idea is if you draw a quantum wave function from an ensemble of certain state, and this ensemble already forms a K prime design, and you use one of the typical state, like a state obtained by large probability, and then generate the projected ensemble, we argued that that projected ensemble forms approximate K design, epsilon approximate K design for K less than K prime, as long as they satisfy these conditions for subsystem sizes.
So for this particular case, this is useful theoretically, but it doesn't have much practical benefit, right? Because you can already, by sampling from different unitary circuits, the outputs are already going to form a K design, right?
Oh, thank you for the question. I mean, like I should have said that. Like, say, what it means is the following. Vedika is true. Like, suppose you can sample from random unitary circuit, and why do we care about generating approximate K design for its subsystem? It's like smaller subsystem, and we can start from the general. We can sample from the random unitary circuit anyway. What it means is, if you generate one particular random unitary circuit, and suppose we cannot tune what the gauge we can apply, but happen to generate a particular random unitary circuit, with a large probability, by just performing measurement on subsystem B, we can generate an ensemble of approximate K design into subsystem. Therefore, somehow like engineer like a controllability or the required amount of quantum control is much less, because it is sufficient to just generate one particular random unitary circuit. In order to prove stuff, this random unitary circuit should be the random particular unitary circuit. But what we believe is that even if you consider like more physical wave function, physical dynamics, say the time-independent Hamiltonian evolution, and we are hoping that the statement will be true, and that's what I'm going to talk about in the next few slides by numerical simulation. Any other questions?
Can I also ask a question? So is there any known like K equals 4 design or more?
Yeah, so if you have a literally random unitary circuit, and then as a function of depth, you achieve high K design, approximate high K design.
Yes. So I heard that it is known that the Clifford gates, they form a exact K equals 3 design.
That's
so
right.
I was wondering if like yeah, like K equals like 4 or more design is known.
Okay, I don't know they have a name, but for any K, the K design exists, and that's known.
Yeah,
and it's not unique.
Okay. Yeah. Another question is that if you have K equals 4 or more design, is that universal for quantum computation?
Not necessarily.
Oh, I see.
Yeah. As far as I know, it's not necessarily the case. Yeah, not necessarily the case. Yeah, I'm not sure about the answer though, to be honest. Yeah.
So it might be like Clifford-like.
It could be. That's right. That's right.
I see. Okay, thank you.
So in the theorem 2, it's the first condition seems to say that A cannot be too small.
That's right.
I see.
So I mean, but we believe that's maybe the artifact of proof, like rather than physics. Yeah. Okay, so let's move on. So we also have a solvable evidence. So for the time-independent Hamiltonian evolution. So in this example, we consider the qubit arranged in the 2D square lattice and consider time-evolving qubits starting from all zero state by the following Ising Hamiltonian. So we have on-site X field and the nearest neighbor interactions. With the nearest neighbor bond interaction, it exists only when this graph is connected. And evolve this initial state by exact time tau, fine-tuned with respect to J0, and also the HI fine-tuned. And consider performing projective measurement in Z basis for all the qubits in B so that we do not measure the last column in A. In this case, we can prove that the projective ensembles supported on A forms approximate K design for arbitrary K with the arbitrary epsilon as long as the size of B is very large. And the idea is that after this particular Hamiltonian evolution, the global wave function of the system forms a universal resource state for the measurement-based quantum computations. And in this case, performing measurement in B is like generating a random unitary circuit, such a way that the complexity or the wave function on A could achieve a high complex wave functions. As long as the size of B is very large, we can achieve like high K design. And this is a solvable limit. But of course, the solvable limit is holds only in a special case of tau and the fine-tuned value of J0. So now I'm going to...
Could you expand on what you need to do? Like what sets the fine-tuning? Like what are you trying to achieve with your fine-tuning?
What I achieve is that you fine-tune the evolution time such a way that this Ising interaction is essentially the same as controlled phase gate.
I see.
And the resultant state becomes a cluster state at that point. And then that's known to be the universal resource state of this.
Okay, thanks.
Okay, so now I'm going to move on to the bunch of numerical evidence. So first evidence is like the unitary time evolution under the time-independent Hamiltonian, which is what's widely studied for the ergodic Hamiltonian evolution, some transverse mixed field Ising model. What we do is we start from this polarized initial state, time evolve under this Hamiltonian, and then we choose the initial state and the parameter such a way that the resultant state is locally infinite temperature, even though the global is a pure state. And then perform measurement on a sufficiently large subsystem B, and then consider the projective ensemble for the A, and look at their statistical properties by evaluating this kth moment state and measure their distance to the kth moment of a Haar random state. And next slide, I'm going to plot this distance delta as a function of time. So here's the result. So delta for k equal 1, different line as a function of time in the log scale. And the different line corresponds to different total system size with the fixed subsystem size, that's 3. What we see is that this distance is decreasing until it saturates, and this saturation value decays exponentially with the total system size or the size of subsystem B that's being measured. In other words, if you take the thermodynamic limit, then this delta will go to 0. And we compare this behavior against finite set of wave functions sampled from the Haar random state, and then measure their distance to the exact kth moment of the Haar random ensemble, and then that's the dashed line. So what this result means is the convergence to the K design state, kth moment in K design is as good as the finite set of randomly sampled quantum state. But this result should not be very surprising because K equal 1 is essentially computing the mean value or the reduced density matrix. So all this numerics basically simply says, our reduced density matrix approaches a maximally mixed state, which is well, expected from the picture of quantum thermalization because we are operating at infinite temperature. We check that this does not hold for when you turn off the longitudinal field, so transverse field Ising model where the system is integrable. Because it is integrable, we convert to the generalized Gibbs ensemble, and does not convert to the infinite temperature, and that's correctly reproduced here. What's surprising is that even if you consider higher moments, say the second moment, or the third moment, or the fourth moment, we essentially get the same behavior. All those distance to the moment decays over time until it saturates to a value that's exponentially small in the system size. And then the convergence is as good as like the 2 to the n b random finite number of random state. And these properties appearing in the high design is not necessarily predicted by the conventional thermalization picture. We are also interested in like the time scale at which we achieve the high K design. So to do that, we put some threshold by hand, like 0.02, and then calculated how long it takes for the delta to below that threshold. And that's why we call it as a, the design time, tau K. And it seems like the tau K increases generally, but mildly as a function of large K. And without proof, I suspect that it might be related to the growth of complexity, but we need further investigations to study whether this statement is true or not.
But we've discussed this, right? You already know this is not true because this is a function of the conservation law. And if you did this for flow K, you wouldn't get an exponential time to form a K design.
No, sorry.
Or this would not show.
We are talking about different time. So the time we talk about is a time until is time that you and I discussed is a time it takes to saturate to the bound, and that grows exponential. However, if you consider non-local model or the flow K system, it decays much faster. Therefore, this does not grow for exponentially long time. I'm not talking about that time. I'm talking about putting a constant threshold delta K over whole system, and then talk about the time, the shortest time that this distance decays. And you can well define this quantity in the thermodynamic limit where everything goes to 0.
I see. Okay.
For that time also seems to depend on K, and that's a separate story. And this is also increasing with the K. Yeah. Or any other question? But this is a speculation, so I don't want to emphasize it too much. But this is interesting. I think it's all interesting observations, but let's see whether it's really the complexity growth or not. I'm open for discussion. Okay, so let's and let me show you visually what's happening. Here I made a video where the subsystem size is just single qubit, and then plotted the projected ensemble as a function of time, and it looks like this. So what we see is that initially what used to be, like clustered is widely spread. And already at this point, they have formed like maybe high design. One design just, one design just requires that their average point is in the middle of the block sphere. But in order to form a high design, we have to guarantee that there's so much uniformly spread over the all block sphere. Okay, so here is the second numerical evidence. Now we take the same model, but instead of considering the dynamics, we diagonalize the Hamiltonian and look at their energy eigenstate. We generate the projected ensemble again, and then compute the distance and then measure its distance to the Haar random. And I'm going to plot the distance to the Haar random as a function of energy eigenvalue. And here's a result. For the K equal 1, 2, 3, the distance is minimized as a function when the energy is in the middle of the spectrum corresponding to the infinite temperature. And we see that feature from all three cases. Now zoom in for the eigenvalues, eigenstate near 0 energy. We only select a very small number of eigenstates. And then consider how they converge as a function of total system size. And again, we see that those are exponentially decaying. So we verify that even for the energy eigenstate, the projected ensemble converges to a universal value. And we believe that this is a property that cannot be predicted by conventional thermalization picture. So we are in some sense just suggesting like high moment generalization of quantum thermalization at infinite temperature. We also have experimental signatures. So we use Ripple quantum simulators in collaboration with the group at Caltech. So we consider the 10 Ripple atoms, and their Hamiltonian is described by this way. This is generically interacting Hamiltonian, non-integrable. We operate at the regime of very strong nearest neighbor interactions, such a way that simultaneous Ripple excitation of nearby qubits, say 1, 1 in the two nearby sites, is energetically prohibited. So that effectively reduces the Hilbert space size of the whole system. And we study the quench dynamics for the all polarized initial state, all zero state, where the system Hamiltonian is tuned so that it's effectively infinite temperature. So what we have done is the following. We consider starting from 10 qubit in the ground state, consider the quench dynamics, and then measure everything in z direction. Unfortunately, we were not able to do the tomography of this projected state, but we could measure everything the z basis and accumulate enough statistics for the z measurements. And then we compute the probability of measuring different B strings on subsystem A, so enumerated by ZA on here, for condition on different measurement outcome in ZB, and we can calculate the B string distributions. And our claim is that this wave function psi condition on ZB is a random state. And what we have done is we accumulate those data for all different ZBs and plot the histogram for measuring B strings, and then calculate their histogram, and compare against this histogram with the Haar random vector. So finite dimensional systems, these distributions for the Haar random vector, it has to follow those formula. In the limit that the dimension of the system, in this case, the dimension is a dimension of the subsystem, is very large, this distribution approaches a Porter-Thomas distribution. By this exercise, we can essentially compare whether the projected ensemble is statistically identical to Haar random vectors as long as the Z measurement is concerned. And here is the result. Let's consider the simplest possible case. Our subsystem A consists of only a single qubit. If our wave function is randomly spread over the block spheres, and then you consider their probability distribution of Z projections, and we expect a uniform distribution. And indeed, we see we recover the uniform distribution from our experimental measurements. For the larger system sizes, this deviates from the uniform distribution and eventually converges to the Porter-Thomas distributions, and we could actually check those behaviors from using our quantum simulators for the 2 qubit and 3 qubit and 4 qubit defined in the Rydberg blockade effective Hilbert space. We can be a little so to see this, we see this experimental histogram, and this black line is basically theory predictions, and we see a nice agreement of the experimental measured histogram and the predictions of the random state. We can be more quantitative. After taking this histogram, we can calculate the kth moment of those histogram. And again, this kth moment converges to a well-defined value that only depends on the dimensions of the Hilbert space for the random Haar random ensembles. And the convergence of this kth moment basically says up to the kth moment, our Z projection measurement is consistent with the Haar random ensemble. And from the experiment, we also evaluate this moment, like a second, third, fourth. And then they indeed converges to expected theory value upon suitable normalizations. But what's more interesting is that this convergence is universal in a sense that independent of which subsystem we choose. So different data points corresponds to different choice of subsystem, either single site or 2 sites, or even 3 sites, whether consecutive or separated. All those cases within error bar, we say they converge to the universal value. So it's a strong signature that we indeed see the projected ensemble behavior that converges to the Haar random state. And this seems to work for all sufficiently small subsystems. Okay, so this is the first part of my talk. We talked about 2 different analytic results, talked about the solvable model and the numerical simulations. In the talk, I talked about mixed field Ising model, but we also talked about geometrically non-local model, or the model that has a U1 symmetry or Z2 symmetry, and also Floquet dynamics in our manuscript. So please check it out if you're interested in. And we also talk about the experimental signatures. But maybe what's missing in this picture is the behavior at the finite temperature. So what if we consider the quantum state that's associated with the finite temperature instead of the infinite temperature? And indeed, we have a preliminary results on that. So to analyze that, the problem of analyzing those the issue is that at finite temperature, there's no analog of quantum state K design. So it's hard to check whether our projected ensemble converges to a certain universal value or not. But instead, we can check whether there exists a certain universal ensemble or not by making a pairwise comparison. So what we do is we consider a pair of eigenstate EI and EJ and consider their projected ensemble and their moment and measure their distance and plot this distance for all possible pairs of energy eigenstates. And what we see is that, at least for k equal 2, those distance is minimized along the diagonal and has a smooth function. And when you plot along this yellow line, basically when the mean energy is away from the zero, so it's not infinite temperature, we said this distance is minimized whenever the energy difference is zero. And at the zero energy difference along this diagonal, we said that the distance is decaying exponentially in total system size. And what it means is that even though we don't know what the ensemble is, actually the projected ensemble at the finite temperature is a smooth function of temperature dependent smooth function. But we are still working on improving for the finite temperature cases. So with that, I would like to change the gear and then move to the last part of the talk, where we utilize the universal properties to design the practical applications. But before doing that, is there any question? Okay, so let's go to the final part. So switching the gear, so we know that now it's exciting time to consider the many different quantum devices. There are many different platforms where you can manipulate the quantum degrees of freedoms. But they are noisy, and then they have a relatively small sizes. And maybe most importantly, they have a limited controllability. Certain quantum gate is easy to apply, but some other gates are the harder to implement in the realistic systems. And in short, we are working in so-called NISQ devices, working with the NISQ devices. And one of the big challenge from the hardware perspective is that it is difficult to actually benchmark our device itself. So what I mean by that is, suppose we want to prepare a certain complicated many-body wave function size 0, applying some time evolutions, either unitary evolutions or something. But in reality, we always have an error, and this error leads to either different pure quantum size psi 1, or we have a stochastic error preparing some mixed state rho 1. And what we want to do is we want to benchmark our device by computing the many-body fidelity between the ideal wave function and the what's experimental prepared. Interestingly, just computing this fidelity itself seems very hard, especially when we don't have enough control to manipulate the quantum devices. And this is one of the bottleneck of calibrating or characterizing quantum devices in today's technology. So let's illustrate why it's difficult by talking about a very naive approach where we do the quantum state tomography. So consider preparing a certain quantum state, say rho 1. And what we could do is we measure all qubits in all three bases, like XYZ bases. There are 3 to the n different basis choice. And for each basis choice, we measure sufficiently many enough so that we accumulate the probability, we reconstruct the probability of getting different measurement outcomes. And each measurement outcome has an order in general 1/2 to the n. Therefore, the number of measurements to reproduce this histogram is 2 to the n, more than 2 to the n, and that's per basis. Together, in order to reconstruct a quantum wave function through this kind of explicit tomography, you need to measure about more than 6 to the n stage. And assuming we have only 10 qubits, which is actually exactly solvable by classical simulations, we already requires like 100 million measurements. And assuming 1 second per measurement, that takes like 2 years, which is way long time. Furthermore, in order to measure every qubit in different bases, we need to have almost a universal control over the systems, at least for the single qubit rotations. And that introduces extra error and noise so that it's not an efficient way to figure out the fidelity. Therefore, now we believe that the full quantum state tomography is way too expensive and is not realistic. But there's an alternative approach by using the so-called speckle pattern proposed by Google. And here is the idea. Suppose we consider applying random unitary circuit, completely random unitary applied to the zero state and followed by measurement in all direction. And what we get is the different probability distributions for the bit strings. They are order 1/2 to the n, but not exactly. They have some fluctuations, and that's why we call it a speckle pattern. Now we consider having a realistic experiment where there's many different errors occurring here and there, either coherent error or the stochastic error. And what's going to happen is that this speckle pattern will completely change, or we approach the uniform distribution corresponding to maximally mixed state. Well, the idea is by simply comparing these two different speckle patterns, you can estimate the many-body fidelity, assuming we applied random unitary. And so they propose a particular way to quantify the degree of correlation between the two speckle pattern called the linear cross entropy benchmark. So here, the P0 is the probability of getting a particular B string Z from the ideal theory, and the P1Z is the probability of getting B string from the experiment. And if you compute this quantity, the claim is this is approximately equal to the many-body fidelity. And what's nice about this particular formula is that now the formula is linear in the probability of experiment. We can replace it with the empirical mean obtained by samples. And this approach is very nice because by replacing this quantity with the empirical samples, we only need to measure a small number of measurements without having to reconstruct a histogram in order to estimate this FXEB. However, there's a downside, which is that we still need to classically compute the probability of getting an ideal of these strings like the P0 of Z from the samples. And also this approach works only when the global wave function is sufficiently scrambled and complicated such a way that we have these B strings at the global level. That means applying this random unitary requires a high degree of quantum control. But we provide the alternative approach to achieve the same thing by generalizing this approach by utilizing the universal statistics that emerges locally that we just described in the first part of my talk. And the idea is this. So instead of random unitary circuit, we just consider the natural Hamiltonian evolution, that's whatever available in your quantum device, and measure everything. However, at least conceptually, we can consider as if we are measuring subsystem A and B separately. Once we measure subsystem B, the subsystem A will remain in a pure many-body wave function. And this pure many-body wave function, according to our claim, will form a projected ensemble that's basically a random vector, random vector. Therefore, measuring A will exhibit the speckle pattern conditioned on the B string measurement on B. Therefore, we can basically repeat the same idea, but repeat it for the speckle pattern supporting the subsystem A. Indeed, we can. This is experimental data. We can consider the probability distributions for the ideal and error case for the theory and experiment. At the relatively short time, when there's a small amount of error, these two speckle patterns are almost like very strongly correlated. But after a long time evolution, when there's many errors, the local speckle patterns are not correlated. And we could utilize these correlations in order to develop the device fidelity. So here's an explicit formula for our method. On the quantum device side, what we do is literally the natural chaotic evolution followed by B string measurement and accumulate as many B strings as possible. And we do not have to repeat this for exponentially long time, exponentially many repetitions, but only the polynomial repetitions for sufficiently long time evolution. On the other hand, on the using classical computer, we calculate the ideal wave functions and evaluate the probability of obtaining each different B strings. And what we compute is a modified formula. So it's similar to XEB, but we have weird denominators that accounts for the locality. Again, this P0 is from the ideal theory and P1 is from the experiment. And similar to the XEB, this can be also estimated empirically by empirical sampling from the experiment. Therefore, we do not require many different measurement outcomes. And our claim is this new formula FC also approximates our fidelity. And more importantly, and this approach does not require any post-selections on the B strings, so it can be done efficiently. And also this is relying on the local speckle pattern rather than the global speckle pattern. So this formula is expected to work even at a relatively short time. We still have to classically compute the probability of obtaining different B strings P0 of Z, and that's going to be the bottleneck of our method. But for the realistic quantum systems, like for relative small sizes, like 10 qubits, I think this is a very suitable approach. So here's actually proof. So this is not an argument, but the rigorous argument. So as long as we assume the formation of local unit quantum state 2 design, sorry about the typo here, and also the operator scrambling, we can show that this FC approximates the many-body fidelity up to exponential correction, exponential in the size of the operator scramble, the size of the region over which the operator is scrambled.
Sorry, so here is Z the bit string only in the A region?
So at the very beginning formula, at our definition, Z is a global Z. But we can rewrite this Z into the A region and B regions, and that's used only in the proof. Did I answer your question?
I guess I'm confused. Like I thought your method is different from the one that's used before because you choose a subsystem.
That's right. So our method is different from Google's method because we are utilizing speckle-Fedon form in the subsystem. However, we managed to write down the formula that does not specify the subsystem. But in order to prove it, you need to rewrite into the subsystem and then show that it works. So our formula is independent of the choice of subsystem.
But when you try to measure this quantity experimentally,
yeah,
the measurement depends on the subsystem choice.
No, it does not. At the end of the day, the protocol is measuring all of these strings, and just use slightly different formula with the denominator, and there's no subsystem dependency in this picture. Only in the proof that we require a subsystem and the formation of local subsystem. And
so the point is that so it's not easier to compute because you still need to do the P0 calculation in the same way as before.
That's right.
So compared to the previous criteria, it's better because you need to do less measurements. Or?
No, the number of measurement will be similar, but it's better because it'll work for globally scrambling dynamics. For example, like it works at a relatively short time. And that's actually my next slide. So we applied our method for random unitary circuit just for the fair comparison. So here, this dashed line is a true fidelity. We artificially introduced some error and then numerically computed the fidelity. And dashed line is a true fidelity. And the solid line is our FC formula. And we show that we approximate F almost starting from this short time. We slightly overestimate, and we understand why. And that's because it takes some time to scramble operators. So it does not identify error before it gets scrambled. But if you use naive XEV formula, it works at the late time when the global system is sufficiently scrambled. However, at the relatively short time, it dramatically overestimates. So the advantage of our approach is the fact that we can work at a short time. And maybe more importantly, our approach also works for the analog quantum similar time-independent Hamiltonian evolution as long as this Emergent 2 design is true locally. And that includes many applications. So here we are relaxing the conditions necessary to apply this one. So here we did the mixed field Ising model, and again the dashed line is a true fidelity, and this noisy line is our approach. And we can show that actually these fluctuations is reduced in the increasing system size. So in some sense, the increasing system size makes our protocol even better, except that computing the P0Z will be increasingly difficult for the larger system sizes. Okay, so I wanted to emphasize that in this way, we can estimate the many-body fidelity without having to apply any fine-tuned quantum control gate. So that's maybe the unique aspect of our approach. So we implemented this idea again using this Ripple-Atom quantum simulator, and here's the results. So on the y-axis we have a fidelity, x-axis we have time. This gray point is our FC formula between our experimental data and our theory model of what we believe that experiment will do. And then we show that this decays over the time scale about like 4 microseconds. But if you theoretically calculate the half-chain entanglement entropy, it already increased at a very short time. So we see that their device actually has a very long lifetime compared to the entanglement speed of entanglement development. This pink line is FC formula between simulated experimental data with the ab initio error model. This dashed line is a true fidelity between our pure model and the ab initio error model. And the reason we have to do this is because it is not possible to extract actual fidelity of the experiment. So we are doing the threefold comparisons using the ab initio error models. So what these results means is that indeed, actually, their ab initio error model, noisy model, well describes their quantum devices. And also the fidelity and FC are almost equal to one another for these parameter regimes. So here we could extract the many-body fidelity without actually performing the quantum state tomography. So this is my second from the last slide. I guess I'm slightly over time. We could use this idea to actually go a little further and then do in situ Hamiltonian parameter estimations. So I talked about this Hamiltonian being of this form. And we talked about comparing the theoretical speckle pattern from what's obtained from the experiment. But what if we are wrong in modeling the dynamics? What if the actual parameters, omega and delta and C6, those Hamiltonian parameters, was something different from what we expected? In other words, from the given experimental data, we could try to optimize our many-body fidelity by changing our model, the ideal behavior. And that way, we believe we can extract the correct parameters, omega, delta, and C6. And here's the result. Y-axis is a normalized over time FC, and this is different parameters. And this gray area indicates the independently measured Hamiltonian parameter. And what we see is that we indeed see that those FC formula is highly peaked when we use the correct Hamiltonian parameter. In other words, if we had not known the true value, we could have extracted those values through our approach. And I think this is a nice outlook for our method, where we can actually extract the Hamiltonian parameter by simple experimental measures. So with that, I would like to summarize my talk. So we talked about projected ensembles and the formation of approximate quantum state K design, and then talked about how to utilize them for the device benchmarking. In the future, we are working on how to generalize this picture for the thermal ensemble. The key theoretical challenge is to define the notion of quantum state K design for the thermal state. It'll be interesting if you can build connection to the quantum complexity or prove the quantum computational advantage of analog quantum devices based on our approaches. Thank you very much for your attention.
Yeah, thank you, Soonwon, for a very interesting talk. We had lots of questions already, but are there any more?
Soonwon, thanks for the talk. Could you go back a couple of slides to where you had the derivation of the
This?
Yeah, this one exactly. Yeah. So that's right. So I think in the second line on the numerator, you would expect to have sum over ZB, P0 of ZB, and then P of ZB, right? If you're just splitting off each.
That's right.
P of Z into P of ZB
right.
times the conditional one. So is there a physical argument why that's a P0 squared? Like, are you assuming that your subsystem is far from the error, or?
Oh, you're right. That's right. Thank you. You have a sharp eyes. Yeah. So here for this proof, we actually simplify the cases. What we have done is, let's assume there's a single error, a single local error, and that propagates to a certain finite subregion, and we define that subregion A, and we assume that we have an emergent 2 design over that subregion.
I see.
Because it only propagates a finite subregion, the probability distribution for P0 is the rest should not be changed. That's why you could just factor it out. Yeah.
I see. Okay. And so do you expect this to still work if you have sort of weak errors everywhere instead of one strong error in some specific location?
No, good question. So each a perturbative, then we can just perturbatively expand and then assume those are different probabilistic error. Our method, actually, I didn't talk about it because it's too much in detail, but if the error rate per time is so large, and then our method will start fail. The reason being, as you said, there will be multiple errors, and then their operator will overlap one another. In these regimes, our approach doesn't seem to work. Yeah, but that's also true for the Google's XAB value too. That's right. Yeah.
Mhm. Makes sense. Thank you.
So a question I have is, does it matter that you are projecting on product states? Like if I take the complement of A and then just projecting on some random state, will it be the same?
I see. So, so when you measure part B, we mostly focus on the local measurement. So it doesn't seem to be it doesn't seem to matter whether it's like X measurement, Z measurement, as long as it's infinite temperature. Of course, if you measure in the contrived, like contrived measurements, say the Schmidt basis, then our thing will not work for sure. So we believe the locality necessary. You mentioned measuring, say, random basis. I think it may be too strong. So I think even if it does not form K-design for local measurement, if you measure in the random basis, it will make them the K-design. So I presume that you are asking this question from the point of view of a little bit of complexity growth, right? So I think the fact that you measure in the random basis already increasing the complexity because your measurement has a large complexities.
Yeah, I was also, I mean, I was asking this question because if I think about the generalization to finite temperature, then probably it matters more if you measure local basis or not.
That's right. That's right.
So the generalization to finite temperature will, I mean, is there a rigorous statement we can make there? If I have a state that you know the energy.
That's right. I didn't put like here because it's a preliminary results, but I can tell you a bit more about finite temperature cases. In finite temperature case, of course, we have to generalize the notion of quantum state K design to finite temperature, which depends on the choice of Hamiltonian, so it's basis dependent. Now you need to distinguish whether the measurement basis is correlated with the Hamiltonian or correlated with the energy or not. So if you measure in a basis that does not reveal any information about energy of the remaining subsystem, then it behaves essentially the maximally random wave functions up to energy conservations. And actually, not only the first moment of energy, but all moments of energy conservation. But if you measure in a basis that reveals energy, you need to subcategorize the measurement outcome so that you group them basically for that such that the subsystem share the same energy, and individual groups will form a maximum entropic state at a different effective temperature for each group. So that's our belief. And of course, this generalized to the generic symmetry, not only the energy. So that's our current understanding.
If you take a many-body Hamiltonian and look at the eigenstates in some window, do the eigenstates themselves form an ensemble? Like not without doing the projective, like do they form a design of some kind?
Oh, I see. That's actually studied by a group of Japanese people. Like there's a paper. I'm sorry that I cannot come up with the author names.
Okay.
But yes, they study, like they consider the microcanonical ensemble of energy eigenstate. It's different from our work because there's no projected ensemble. But they consider the moment of those ensemble.
Right.
And they argue that they form an approximate K design in a particular sense that the matrix element for the like local or particular set of physically simple operators looks as if it's a K design. But we know mathematically that they cannot be actual K design or even approximate K design for all operators.
Right.
Yeah. So there are some results on that. I can forward you the link to the paper.
Okay, thanks. Yeah.
It's the same as this. Like if you have a microcanonical ensemble and they're considered their equal mixture, like the just first moment, and then consider the subsystem, it looks maximally mixed. Actually, you need only one eigenstate to do that. The same way, like if you take the kth moment, if you study the subsystem, it'll look like, maybe I should have said that. Like maybe that's slightly different, but it's not only about the subsystem, but the sort of certain set of observables, they behave like K design, but not for all observables.
Right. But I guess it raises the question of how, because in some sense, infinite temperature eigenstates, right? They can show page entanglement entropy. Like if your Hamiltonian is thermalizing, in many ways they look like random vectors, even though they're not exactly random vectors.
That's right.
So I would imagine that you would have to, you know, and if you're doing this microcanonical energy window at infinite temperature, I would imagine that you may have to do something like, well, yeah, like I can't think of something obvious to check that says that, you know, this is obviously not, you know, that this was a many body eigenstate. Like if I gave you a many body eigenstate and an infinite temperature kind of Haar state, right? What's the minimal thing I would need to do to be able to tell that this was an infinite temperature eigenstate versus a Haar state?
No, I agree.
Or something sampled from the Haar.
That's the question we are addressing. So I don't know the answer, but that is a relevant question. Say, we know up to any linear observable, the expectation value of any linear observable will look as if it's an infinite temperature. So it will not distinguish whether it's a pure energy eigenstate or like maximally mixed state. Like, okay,
not really. I mean, if the Hamiltonian is local, then if you can measure the expectation value of local operators very precisely, then you can actually figure out that it is an eigenstate of the Hamiltonian.
That's actually true. Yeah,
so this is your getting the Hamiltonian from one single eigenstate. Yeah.
But of course, I mean, that requires you to know that eigenvalue property. I mean, it requires you to know the correlation matrix very precisely.
I see. That's actually true. But there you break the locality because you need to measure the 2-point correlation function.
Yeah, but that's still K-local. Like it's a small subsystem. It's a small subsystem that's not a geometrically local.
So yeah, okay.
That's actually a very good point. Yeah. Actually, if the Hamiltonian is promised to be geometrically local, you also need to measure only the geometrically local ones, right?
No. I think you still need a correlation between the 2-point function between these local terms.
Even for the distance term?
So Xiaoliang, I guess
you need like if I give you these are the allowed terms in the Hamiltonian, then you need to study like connected 2-point function between any pair of them.
Yeah, but let's say the allowed term is only the nearest neighbor interaction, for example.
And then you need to study connected 2-point function between these nearest neighbor terms.
That's right.
Between the terms that are drawn from this set, so it's still not local.
Yeah. But it's
yes, I guess right? That's what I was gonna. Yeah. So Xiaoliang, I guess my question was, at least from what I remember of the method, like if I have some kind of basis of things that I build my Hamiltonian from, right? Suppose I say that, you know, okay, I have ZZ type interactions of 2-body and 3-body terms and so on. Then I can build this correlation matrix and see and solve for like if some coefficients of that kind can give me this as an eigenstate, right? Okay. Yeah. But suppose I'm just allowed to say that any 2-body all I know is that my Hamiltonian is 2 local, right? Or even spatially local built up of 2-body operators, but the 2-body operators can kind of point anywhere on block space, you know, so it's some spin and some other spin. Then do I have a way of doing that? Like,
yeah, because the only thing you need is the subspace of operators that are allowed. So yeah, you just choose all polys, which will be like 9 for the nearest neighbor.
Yeah. I see. Oh, okay. I see. Okay. So you're saying that anything can
you just need a linearly independent.
Right. Okay. Okay, good. So basically what we wouldn't be able to rule out, like you could at least keep checking more and more non-local things and see did it come from there or not. Yeah. Okay.
I think the distinction is this. I give you a pure wave function, but I'm not going to tell you that it is an eigenstate of a certain Hamiltonian. I do not have that guarantee. And can you still distinguish whether it's a mixed state or a pure global wave function without knowing that it's an energy eigenstate? Okay, so the reason
I think that is a question, right?
Yeah, that's right. In that case, I think it's essentially the complexity, the way to formulate the complexity. You know, how this pure state is distinguished from the maximally mixed. What is the minimum depth or that number of gates you need to apply in order to distinguish them? So the reason that Xiaoliang's example works is I have a knowledge. We know the knowledge that it could be either eigenstate of local Hamiltonian or not, and we are utilizing that feature. But without the knowledge, it'll be difficult. Yeah. In other words, say, suppose you have a random linear combination of energy eigenstate within a small window. And this approach will not work.
Mm-hmm.
Yeah, but maybe actually we can generalize a little bit. If you know, if you are given that it's a linear combination of less than a certain number of energy eigenstate, I think we can work it out a little bit.
And probably the variance will be bounded in
Yeah,
some
that's
way.
right. Exactly. So that it depends on how many eigenstates are forming random state, and that way we can, I guess, we can deduce it. But yeah, it's more about knowledge about whether we know it's an eigenstate or not, I think. Yeah.
Right. So Shaoliang, how would I put this in like words? Because it's like, if I just look at it, somehow this whole correlation matrix, right, that enters, because if I just look at a 2-point correlation, that'll agree with like the Haar state, right? But any one, or not agree, like.
Actually, the particular one will not. So basically, what happened is that if you define an energy density operator, and then you study the 2-point correlation of that, the connected 2-point correlation, there is a small deviation from the Haar random state because the state is conserved. So so the sum of that is energy. So the sum of that must have 0 fluctuation. So therefore, there is a slightly negative correlation between energy density here and energy density here. Yeah, that's what happens, which gives you a deviation. It's a polynomial thing, like the deviation is like 1 over system size. It's not a, but I think so it just means that if I don't tell you whether the state is a ground state is the eigenstate of a local Hamiltonian, as someone said, you can try this. You can try this algorithm for operator size 2 or operator size 3 and so on. But the chances for most of the random states, all these will fail until you go to like half system size.
I see. No, actually, and when I first read your paper, I was thinking about whether something can be generalized also for unitary systems like Floquet systems, and that didn't really work. And I think this is one, because you could ask, like, if you have an eigenstate of a Floquet system, how do you tell that apart from a Haar? And your thing doesn't work quite there, and now there's no energy conservation, so this approach doesn't. Yeah.
I see. So it's we are utilizing the conserved quantities very smart.
Yeah. Because indeed there's going to be correlations between the conserved densities that's important. Yeah.
Thanks, Soonwon, very much. That's really helpful. Yeah, I need to go offline now, but it's really interesting.
All right, thank you, Shaoliang. See you.
Right.
Yeah.
Okay. All right.